Hello everyone, welcome back. This is a video for my Method 25 like supplementary materials. And today here's page 4. So today we're going to talk about like section 5.1, which is like Riemann Sum Theory that 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 this topic it is an introduction to like approximating the area under like under a specific under a function. So section 5.1. It's a Riemann Sum Theory. And why we introduced Riemann's theory, it is because method 25, it is integral calculus. Is like we to approximate or compute the area between the curve or under the curve. And the Riemann sum introduced the method that we cut a specific region, we cut a region into n sub intervals, or a big interval, into or big intervals into many small subintervals. We use it to approximate the area. And how they approximate this, we have the width. Perhaps we have interval. A and B. And a function f of x. And now we want to know what is area from A to B under the curve of f of x. Since we had not learned any integration technique yet, so we use Riemann to approximate. So we have like the width. It is delta x, and is equal to b minus a over n, and what we have, it is just try to adjust this. There's like the screen, so I can just see what else. And to the ith, like this subinterval, it is equal to a plus I delta x. And for example, here, we we can approximate the area under f of x equals to x squared from x equal to 0 to x equal to 4. And there are 3 different ways we can approximate. And the first method, it is the right endpoint. So perhaps it's the same function and the same interval. And actually, by the way, like Riemann sum can be wrote as this. So it's like we call them as like Riemann limit. It is infinity here, and we use the right endpoint. We have perhaps the same function, perhaps f of x, it is x squared. Then interval is from interval is the same interval, but this time we use 5 subintervals. Then we have like delta x. It is 4 minus 0 over 5. It is 4 over 5, and is our width. Each rectangle or each subinterval is 4 over 5. So we use the right endpoint. So we start from the upper bound of each subinterval. So upper bound. So we take x equal to 4 over 5, 8 over 5, 12 over 5, 16 over 5, and 4. We write notation as R4 is our, it's R5, our notation is equal to the limit x approaches infinity. A sigma notation here. what we have, like that H is a 4 over 5. It's gonna be start right point is, so it's gonna be F of 4 over 5 plus F of 8 over 5, have F over 12 over 5, have F over 16 over 5, and F of 4. Then we compute its value and we just multiply it up here. Plus 16. This is 80. This is 100 form 80. 880 plus 20. This is 220. So it's 176. But well, 80 plus 400, 480, 120. So 176. It's our right-endpoint. So it's the right-endpoint is our first method. Even have a larger outcome because you have like a larger area just above the curve. We usually have larger output. And which we call overestimate. And as n is number of interval increasing, then the output will be more accurate and near the exact area or the exact number. The output tend to be more accurate. Page 5. Now it's like another point is the midpoint. So the midpoint, we have the same subintervals, but we took the middle value of each interval, of each subinterval. to approximate the area under the curve. So for example, it's the same function, f of x equal to x squared is interval from 0 to 4. This time we are doing 8 subintervals. To find the width of each interval of each subintervals. So we compute delta x. It is 8 minus 0. Oh, jeez, wrong. It should be 4 minus 0, not 8 minus 0. Over 8 subintervals, we get 1/2. It's our width. So we would take x equals 2. This is 1/2. So we take 1/4 and 3/4, 5/4, 7/4, 9/4, 11/4, 13/4, and 15/4. And this is, and for this is gonna be the midpoints will be right mid 8, M8. Here's notation here. We have is 1/2 over f1/4 plus f3/4 plus f5/4 plus f7/4 and let me plus f15/4. So we have it is, I'm just gonna do the computation by hand. So it's gonna be 1/16 plus 9/16 and plus 25/16 have 49/16. We have is 81/16. We have is 121/16, 169/16. Finally, we have 225/16. $35 plus 49, 84, 81, 165, 165 plus 121, 286 plus 169, 455 plus 225. 680 divided by 16 should be 42.5, so it is 2/85. Oh, so 85 over 2. So it's 85 over 4. Should be 21.25. Actually, I have to check my answer on the back side of it. So we have 80. This is going to be 400, 480 plus 880. 880 over 25. Should be just 300. This would be reasonable. I'm so sorry that I don't know how that came to 880 divided by 25 is 220. I'm so sorry for the mistake. This is really pretty good. Now we're gonna do another. The third method of approximation is a left endpoint. It's a left endpoint approximation. So we take the lower bound of each subinterval to approximate the area under the curve. So perhaps it's the same function again. Same interval. We are doing 5 subintervals. And then the width, it is 4 or 5 again. One we do 6 intervals, and we try to remember. So like the interval subinterval should be 4 minus 0 over 6. It is 2 over 3. And we take a 0, 2 over 3, 4 over 3, 2, 8 over 3, 10 over 10 over 3. That's all. We compute is the notation is just L6. x approaches infinity, and I equals to 1, there's f x I minus 1, and then is a delta x. We have it as 2 over 3. It'll be f0 plus f2 or 3 plus f4 or 3, and then plus that f2, then plus f8 over 3, then plus f10 over 3. Then what we have it is 2 over 3 is like a 0 plus 4 over 9 plus 16 over 9 plus 4 plus 64 over 9 plus 100 over 9. Nine over 900, 220 over 9. $440 over 27. I'm gonna maybe like 15 or 20 or whatever it is. $16.29. So we can see the area, it is higher than 16.297, while it is lower than 28.167. So I can assume the midpoint approximation is the most accurate method that we can use to approximate. And as we approximate more subintervals, the result will be more accurate. Now we're going to talk about like how to write a notation for like Riemann sum. Perhaps we have a function is f of x over the interval a and b. And for like a step 1, subintervals. And like the width. The width is noted, it is delta x is equal to b minus a over n in subintervals, always to make sure that n is not a 0 or 1. And pattern x as x to the subscribe 0, it is equal to a. Then x1, it is a plus delta x. The x subscribe 2, it is to a plus 2 delta x. And then the xn, it is b, is the upper bound of the interval. And then, and the step number 2, choosing the approximation method. If we have a right endpoint, then the inside of the ith interval, subinterval of x, it is xi. If it's a midpoint, we have x bar of I, because the x bar, it is average, so it's the midpoint of each subintervals. And for the left point, for the left endpoint, it's minus, because it x minus I minus 1, because we approximate from the lower bound of each subintervals. The construction, the last step is the Riemann sum construction. If we do right endpoint, it's Rn is equal to this sigma notation n I equals to 1 f of x I delta x is equal to delta x over x1 plus fx2, then plus fxn. Then for like a midpoint, f x bar over I, and then it's a width. It's like then the width is the delta x. We have it as f x bar 1 plus f x bar 2. Let's put we have it as f over f of x bar n. Lastly, is the left endpoint, have its sigma notation. It is f x I minus 1 delta x. So we start from the lower point, so it's x subscribed 0. plus 1 plus x1 plus plus f of x and minus 1. Here's the most boring part of it. Let's do another example here. If you have a function f of x, it is 2x to the cubic and a plus squared minus 4x over the interval of 0 to 10. Then approximate with midpoint with 5 subintervals. Area with midpoint rules and 5 subintervals. So try it on your own. Perhaps this is on the exam, and I believe you can do everything on your own later in the quarter because you have to take the finals. I'm not taking final for you, but because it's your ability to show what you know and earn what you have. I'm just here to help you, but I'm not going to take tests for you. I'm not going to take tests for you. So it's your job to learn everything. I'm just help you. I'm just as like student helper. I'm gonna do my best to help you and have to learn less painfully. So let's roll. Here we have delta x. It is b minus a over n. We have 10 minus 0 over 5, which is 2 is over width. It's just a midpoint. Let me take x to 1, 3, 5, 7, and a 9. Then midpoint notation is here we take M5. X to 1, so it's f x ri delta x. It is 2 f1 plus f3 plus 5 plus f7 plus f9. So we have it is 2 times 1, so it's 1 plus 3 minus 4 is it is negative 1 plus 3, 27. 54 plus 9, 63 minus 12 is 51. The 5, 125, 250 plus 25, 275 minus 255. Plus 7, 336 plus 49, 336 plus 49. The 385 minus 28 is 357. Plus 9 is 729, 1,458, and then plus 81. Minus 36 It is 1503. 50 plus 255 plus 1503 plus 357 2165 plus 2 is 400. The total, the final answer should be 4,330 is our midpoint approximation. If you do right-endpoint, and let's try it. If you do right-endpoint, in this case, we would take x equal to 2, 4, 6, 8, and 10. Then R5, it is like sigma notation, f of xi dot x, it is 2, f2 plus f4 plus f6 plus f8 plus f10. Now what we have it is 2. This should be 1620 minus 12 plus 4. This is 128 plus 16 144 minus 128. 6 is 216 432 plus 32 is 468 minus 26 442. 8 is 512, so it's 1024 plus 64, 188 minus 32, which is 1056. Plus 10, it is 2000 plus 2100 minus 40, 2060. And what we have is 40 plus 120, 442 plus 1056 plus 2066 0 is 309.2. So we have it as 7,196. That's it. It can look, it is a way larger, so it's overestimate. I think that's all for 5.1 lecture Riemann theory. For next will be 5.2. It's a definite integrals. And thank you everyone for watching and have a good day.